This is what a differential pair looks like. So this is some bias current I0, and we have a source coupled pair formed by M1 and M2 and load resistance is R. So normally we use this as an amplifier. Let's say how we use it as a logic gate. Okay. So the input is applied here. That is, the difference between these two voltages is the input, and let's say the difference between these two voltages is the output. Okay. What kind of logic gate is it? What sort of logic gate is it? Inverter. So where is the inversion? What is the input? In P minus in N. Okay. What is the output? So firstly, the one thing you have to realize is when you have differential signals, explicit inversion is not necessary. You can simply swap the wires and that gives you the opposite logic. Okay. So whether it's analog or digital, you don't need a gain of -1 if it's analog, or you don't need an inverting logic gate if it is digital. You simply swap the wires and you interpret it negatively. So the way I have drawn the signs here, it is a buffer. Okay. So if you have some input, it will give you the same logic output. And if you want an inverter, you simply swap the output leads. And one of the first things we do when we have a logic gate, for instance, when you have the CMOS inverter, is to draw the input-output characteristics. Okay. So here, this is the input, and the output is V out P minus V out M. What does this characteristic look like? I just want the output versus input. What does it look like? Huh? Straight line. Okay, what is it for input equal to 0? 0. So when the two inputs are at the same voltage, what happens is the two transistors conduct equal current I0 by 2, and the voltage drop at the resistors across the resistors is the same, so the difference is 0. And what happens if I increase this positive difference? More current flows through M1 and less through M2. Okay. So this potential rises up and this falls down. Okay. So it increases like this, and if you make V in P minus V in N negative, it goes in the other direction. And what happens? It will keep on going like this. Saturates. What is the value at which it saturates? VDD minus I0 R. VDD. When it saturates when all of this current I0 flows through one branch. Okay. When the input is large and positive, I0 flows through the left M1. So this is at VDD minus I0 R, and this is at VDD. So the difference is I0 times R. Okay. And on the negative side, it saturates to minus I0 times R. Okay. So this corresponds to a logic 1 and this corresponds to a logic 0. Okay. Is this okay? So if you need to brush up the operation of differential pair, please do so. What is the input voltage at which you have saturation? What is the input voltage beyond which the output is plus I0 R? What is the input voltage beyond which it's plus I0 R? Why are we even trying to calculate this? What is the significance of this? Huh? Okay, so first let's say what is this value? What is the value of the input beyond which it saturates? overdrive voltage of M1 when I0 is flowing through it. Okay. So when all of the current is just here to one side, let's say M1, there is I0 flowing here and 0 flowing here. I am assuming that this voltage is such that M2 has just stopped conducting. Okay. So the voltage across the gate and source is just the threshold voltage, whereas here it is the threshold voltage plus 2I0 by mu CMOS W by L. Okay. Where W and L correspond to the transistor M1. So the difference between the two is simply the overdrive required for M1 to conduct a current of I0. And what is this? What's the value below which the output is minus I0R? Just the characteristics are symmetric, so this will be minus square root of 2I0 by mu CMOS W1 by L1. Okay, so what should this voltage be? How much should it be? As small as possible. Why? Delay? No, there is no time dependence here. Okay, so why do I want that? Okay, what should it be in relation to I0R? Should it be smaller or larger than I0R? Or can you make any comment on it, or are the two unrelated? Why is that? So, if you look at any logic, right, you need gain in the logic circuit. The level difference between the logic levels at the output should be more than that at the input, because the assumption is that you have similar gates driving each other. If you drive a gate like this using another gate like this, the levels of that must be definitely sufficient to swing the logic of this. Okay. So the spacing, this vertical spacing will be the input to some other logic gate, and that should definitely be more than this one. Okay. Because when it's operating as a logic gate, we want it to operate in this region and in this region, not here. So anything that we say is an acceptable one, that should be here. Okay. So basically we can say that any voltage in this beyond this is considered a logic 1, and any voltage below this is definitely considered a logic 0. The voltage in the middle, there is some transition, so it is not 100% clear. Okay. Especially if you go very close to the origin, it will not be able to resolve the logic. So just for simple functionality, this I0R should be greater than the overdrive voltage of the transistor. Because if you cascade a bunch of gates, what happens if this is less? If this condition is violated and you cascade a bunch of gates, what will happen? It will not be self-restoring, which is the most important thing you need in a logic gate. Okay, you need some gain. Even if you have a gain of 1.01, you can eventually make a logic family out of it. But if you have 0.99, it will eventually die out and you can't restore the digital levels. The digital noise immunity, etc., comes from having this gain. Okay. Yeah, this is an open loop. No, I mean, what else is a comparator? This is a comparator, right? So a comparator also has a similar characteristic. It has some gain, and it has some area where it won't resolve the input into either 0 or 1. Okay, this is a comparator. So in a given technology, what do you have to do to achieve this? You are designing the circuit, right? So what does circuit design mean? You choose the values of W and L and R and I0. Okay, how would you choose them? So okay, we already said that this threshold voltage, this overdrive voltage, must be as small as possible. Okay, so how small do I make it? Do I make it 10 millivolts? Okay, but what prevents me from going as low as possible? But what is the effect of having, see, I can satisfy this inequality by several means. I can increase W1 and L1 a lot, W1 by L1 a lot. I can decrease the value of I0 perhaps. Actually, decreasing the value of I0 won't help. Okay? I can increase the value of W1 and W1 by L1. Okay, let's say they are in saturation. How is the saturation related to this? I understand that, but if I keep on increasing W1 by L1, will it go out of saturation? Actually, there is a constraint and a higher constraint also. If you keep on increasing W1 and L1, the input capacitance will keep on increasing, right? So again, I am assuming that this will drive another gate like this. So you set out to build a high-speed logic family, but then you increase the load capacitance of that a lot. That's pointless. So that puts an upper limit on what you can do, right? You can, as you keep on increasing W1 by L1, the characteristic will become steeper and steeper. But then if you keep on doing this, the input capacitance keeps on increasing. So it's rather pointless to go on doing that. So you have to choose some compromise where it operates at a high enough speed. At the same time, it has enough restoration of logic. Okay. Yeah. Okay. You can increase I0. What happens then? Yeah, that's true. So you can do it to some extent, but then you are burning more power. Okay. And there are some other conditions you need for this to operate properly. So far we only concerned ourselves with V in P minus V in N, the differential input. Is there any constraint on the absolute value of V in P and V in N, or the common mode voltage? So what is the constraint? The current source should remain in saturation. This is M0, M1 and M2. Okay. So what is the constraint for it to remain in saturation? It should be greater than what? Vt plus Vd sat of M1, M0. So firstly, are we supposed to see V in P and V in N both have two logic levels? Okay. So V in P and N are the common mode voltage plus or minus some differential voltage. Okay. Which is the worst case? When V in P and V in N, like one of them is high and one of them is low, or when the two are equal? What is the worst case for M0? Is it when V in P equals V in N, or when V in P is different from V in N? When current is totally steered to one of the transistors, it's the worst case. Why? That's when the source will be the lowest. Does everyone agree with that? The source he is talking about is this tail node. He says that when one of the inputs is at logic high, the other one is at logic low, the source potential is the lowest. What is the source potential as a function of the difference voltage? So in fact, has any of you analyzed this? Have you seen this before? The variation of Vs as a function of the input differential voltage? When is it lowest? How does this vary? So it turns out, again, I'll leave the analysis to you. It will be lowest when V in P equal to V in N. Okay? It will be an even function like this. Okay? What is this value? What's the lowest value? What is the lowest value? When V in P equals V in N, it's assumed that it is equal to the common mode voltage. Okay? So Vd equal to 0. That's what it means. So this voltage is V in Cm minus. So it's the Vd sat of M1, Vd sat of M0, okay, minus Vd sat of M1, but this is when a current of I0 by 2 is flowing through it, okay. This is different from the Vd sat we discussed in the previous case where all of I0 was flowing through M1. So it's basically VICM minus the overdrive of M0 when I0 is flowing through it, minus minus the threshold voltage of M1. Okay. Oh, sorry, not this. Just VICM minus the threshold voltage of M1 and the saturation voltage of M1 when I0 by 2 is flowing through that. And this should be greater than saturation voltage of M0. Okay, this is the condition. Is this okay? If you don't understand this, let me know. I'll explain it again. This, which part of it? How the voltage varies or the condition? How the voltage varies, you can do the analysis and find out. It will be an even function. The one intuition I can give you is when one side is completely off. Let's say this is off. This, you have this circuit, okay? You have M1 and M0, which is a current source. What is the circuit? Huh? No, I mean, if this, you consider this as the input and this as the output, what is it? Source follower. So, the output simply follows this voltage, okay? So, when this is cut off, it follows the voltage of M1. And when this is cut off, it follows the gate voltage of M2, okay? So, it does this, and on the other side, it does this, okay? So, this is, if there is no body effect, this is a line of slope 1. And in the middle, it does something like this. The equation for this curved part, you can derive it by writing the square law relationships for M1 and M2, okay? So, I hope it's easy to convince yourself that it is an even function. It is symmetric, right? It can't distinguish between V in P or V in N. So, it has to be an even function. So, anything on the line of symmetry in a differential circuit has to be an even function with respect to the differential input. Okay, so this is one of the conditions. This is the lower limit on the input common mode voltage. Is there an upper limit? What is the limit? What is is there an upper limit? If there is none, just tell me that there is none. VDD is the upper limit. Okay, there is no risk of any transistor going into triode region also. Now the common mode voltage, see, this is a logic gate. The way it works is, if this is tied to logic 1, this is tied to the input common mode voltage plus VD by 2, this node will fall down and that will go to VDD minus I0R. So this is the gate voltage and this is the drain voltage, and there is a definite relationship, that is the gate voltage should not be above the drain voltage by more than a threshold voltage, okay? So this depends on the differential swing also that you apply to the input. Why do we need it to be in saturation? Why? Why do we need a differential pair transistors to be in saturation? We want gain. What happens if we don't have gain? Or rather, why will we not have gain if it's in triode region? So, let's go back to the characteristics we saw. This was the characteristic of the differential pair. Assuming it was in triode region, what do you expect will happen if it's in, if it's in, this was in saturation region, what do you expect will happen if it's in triode region? So, see, it reaches saturation when all of the current is steered to one side. Now, to carry a given current, if it's in saturation, you need a certain VGS. If it's in triode, you need more VGS. So, that means that you need a larger swing to turn the differential pair one way or the other. So, that's why you need to have it in saturation. And another way of saying it is you need more gain. Okay. Okay. So, given that we need M1 and M2 in saturation, this is the condition. What is this? VICM plus VD by 2 is nothing but the high logic level at the input that appears on each of the wires. And that should be less than the drain voltage plus the threshold voltage. What is this? What is VICM plus VD by 2? Well, what's a reasonable value for that? Remember again, this is a logic family, right? You have logic gates driving other logic gates. I0R. Now, is the question clear? This side is the high level voltage that appears on each of the input lines, okay? And this side is of course some voltage that is based on this circuit analysis. Now, what is the reasonable value for this voltage? VDD, right? So, when this logic when this logic gate is giving you a high output, one of these is at VDD, the other one is at VDD minus I naught R. So this is nothing but VDD if a similar gate is driving this. Okay. So what is the constraint now? Yeah, it is VIP. What is the value of VIP? So a similar gate is driving this. Okay. So when the output of this gate is, when it's high, one side is at VDD, the other side is at VDD minus I naught R. So here we are looking at the higher voltage. So that should be VDD. Okay. So this means that I naught R is smaller than VT. This is another constraint on the choice of I naught times R. Okay. Okay. So what happens if you do that? So what you're saying is true, and sometimes you do use it like that. You make a compromise. So what happens if it's not in saturation throughout? I mean, what's the effect on the characteristics of the gate? So basically you need more voltage to switch it completely, that's all. So we'll start with the assumption that it has to be in saturation. And in fact, you do design it in many cases where it has to be in triode simply because you can't do it otherwise. Okay. But it is best if it is in saturation. Now, so this we get as a constraint I naught R less than VT. Now this is something that's dependent on I naught and R. This side is something over which you have freedom, right? You choose I naught and R. Or this is something that is dependent on the process. Okay. So you may or may not have freedom over it, and it also changes over process and temperature. Process variate corners and temperature. So you'd have to take the lowest value over all the process corners and temperature to remain in saturation region. Okay. So what if this is not possible? Let's say VT was very small. So if as VT reduces, you have a problem with this. Okay. You have to make I naught R smaller and smaller. But then if you make it very small, you may not be able to switch the next logic gate. So what can you do in that case? Is there some, no, let's say I don't want to make a compromise. What is the circuit solution? I mean, you don't have control over the process, right? Here we are talking as designers. So we have only we have freedom to change the dimensions of the transistor. We have freedom to change values of resistors, etc. But you don't have control over the threshold voltage or any of the process parameters. No, the body is already connected to ground. You can't pull it any further. No, I mean, it's a simple circuit, right? What is, the constraint was really between VICM and this. So what do you have to do here? Insert a level shifter before this, so that the input should not go all the way to VDD, that's all. So a simple level shifter is a source follower. So you may have to do this, okay. Well, that depends on the value of the supply voltage, okay. What is the constraint now? We have to just reevaluate the constraints, okay. Okay. Now this is again driven from a similar gate. What is the value of this? VICM plus VD by 2? Huh? VDD. What is the value of this? VDD minus I naught R. Okay. Now what are the constraints? We can reevaluate the same constraints. What is the constraint for M0 being in saturation? Anyway, I am not going to go through this because this is really a simple circuit analysis, right? You have the VGS of this and the VGS of this. So the input minus all of these VGSs should be such that M0 is in saturation. And as before, the constraint is when the two voltages are the same, not when it is skewed one way or the other. Okay, that is the worst case. And now actually we came up with this circuit because M1 was going into triode region. That was the motivation for us to come with this circuit. So what is the new constraint for M1 being in saturation? Or when will M1 go into triode region in this circuit? So when this is at VDD, the voltage here is VDD minus VD start of M3 minus VT of M3, and what should this be? This should be smaller than this voltage plus VT, VDD minus I naught R plus VT1. Okay. So what does it mean? So this was the original constraint, and that this much has been added to it. So you have a lot more freedom now. Okay, and in fact, if you see somewhat higher voltage versions, this is the way the circuit is used. Okay, and the source follower also works as a buffer and helps you in some extent. Okay, so the basic constraints can be evaluated. So if you can have, if the levels are not convenient, you do level shifting. But the idea is you have a logic family, so the input level should be compatible with the output levels. Okay, so that you can connect one logic to the other, one logic gate to the another. Otherwise, you can't use the logic family. Alright. So what was and of course it's trivial to see that the supply current is a constant because this is a current source. Okay, the current through the supply and ground is always constant. Okay. So that actually got rid of one of the problems of CMOS logic where the switching current was flowing through the supply lines and you were having problems because of that. Okay. And also it is a differential circuit, both the inputs and outputs are differential. So it gets rid of the crosstalk problem to a great extent. Okay. And the reference problem, that is the output is measured as the difference between these two, not as between this and some ill-defined ground. Okay. So that problem also has been got rid of. So, but so far we have only a buffer and an inverter. Inversion is free because you can swap the wires. How do I make more complicated logic with this? I want to make an AND gate. What do I do? So let's forget these source followers, right? Let's consider just this version. Okay, that is just an extra detail. We can always add it to every input if we want to. So let's look at this. This is a buffer / inverter. Okay, and I want to make an AND gate. What do I do? Is it possible? How do you construct an AND gate in CMOS logic? Huh? So you start with an inverter. Okay. How do I turn this into an AND gate? Okay, let me, for simplicity, take an AND gate because that's simpler. How do I make this into an AND? I'll have series NMOS and parallel PMOS. Okay. So can we do similar things here? There is no PMOS. What do we do? Parallel NMOS. So this is A, Y, AP, AN, YN, YP. Okay, for an inverter, this is the polarity. What do I do now? I have to get this function. Forget about whether it works well, triode, saturation, all of those things. But I want differential input, differential output circuits, and Y should be. And the logic that you follow is similar to this, meaning here you connect NMOSes in series, right, and PMOSes in parallel. So what do I have to do here? So, which NMOS? Okay, M1, M2. What do I do to M1? What do I do to M2? What do I do to M0? Okay. Is this what you want? And what do I do with signal B? Does this work? What will be the output voltage? What will be these two voltages? What will be YP and YN? It should be BP and BN. What will be the output voltages here? YP and YN? No, not in any condition. This will never be on, right? Huh? Yeah. AP and BN are high, there will be a path. What will you get? Like I said, what happens if this is low and this is low? So both the outputs will be at VDD. This is not actually implementing a logic. B to M0. I want differential input. Yeah, that's actually a clever thing. Let's just quickly see what happens if you do that. So he says you apply B here. Okay. We don't know what the logic levels are, what voltage levels the logic levels correspond to. Okay. Let's forget that. What function does this implement? So this is an interesting thing which we'll use in the next case. So let's forget this. Let's focus on this one. So this won't work, but how do I do it? How? Because it's an XOR gate, you can do it. Okay, let's hold off on that for a moment. Now, what is the idea here? Like, one second. So we went from here to here to get a NAND gate. What is the idea? Why did we connect NMOS in series and PMOS in parallel? Yeah, but why is it in parallel? Why is it in parallel? No, I understand. You are describing the logic function. Why is the NMOS in series and PMOS in parallel? No, that's correct. But so if any one input is 0, the output is? Okay, so what can we do something similar here? Okay, how will that help?
If both are high, sir,
Yeah.
then the phi k will be high compared to phi n.
Yeah, what about if one is high and the other is 0? So the logic is similar to this. If something is controlled by a low voltage, so here both of these paths have to be on for the current to flow on this side. Okay? So on the other path, one of the two should be on. Okay? That's the idea. That's the idea here, and the similar idea has to be here. Okay? Is this clear? So this path is active when both AP and BP are high. And this path has to be active when AN or BN is high. Does this work? So this is analogous to connecting the PMOS in parallel. Okay, so you can construct any other gate. And of course, if I interchange YP and YN, I have the AND function. So inversion is trivial. And if I interchange the inputs, I get an OR function. Basically exactly the same circuit does OR, NOR, and NAND. Okay? Because the inversion is trivial, you can interchange the output or interchange the input to get any function you want. Okay? So basically we implemented AB, so you can implement A bar, B bar, you can implement AB bar, and you can implement this. So basically this is AND, NAND, NOR and OR. Okay. So the same gate does all of them. Is this clear? I mean, is everyone convinced that this implements the logic function that we want? So if you want to implement logic, this is how you do it. Now, one of the things to notice, I think in this, there are various combinations of transitions. Like you have two inputs, so you have 4 states, 0, 0, 0, 1, 1, 0 and 1, 1. And during some transitions, not all transistors will be in saturation. Okay? But that's okay. I'll leave the circuit verification of this to you. I'll have some problems in the assignment to verify that. Okay? Okay, so what is that? What function is that? What he's referring to is an analog multiplier circuit. So if you have V1 and V2 as inputs, you get V1 times V2. What kind of logic is that? What is the logic function implemented by? What is the logic function that's analogous to multiplication? And? Huh? Why is it and? Okay. Yeah, that's right. So I'm saying similar to, right? So if I have to write the kind of truth table for a multiplier, this is a multiplier. Both inputs can be positive. These are the combinations. What do you get? What do you get here? Plus, minus, minus, plus. So this is an XOR gate or an XNOR gate. Okay. So what you can implement with an analog multiplier is an XOR function, exclusive OR function. If the two have opposite polarities, which is like saying two have opposite logic states, the output will be in one way. If the two have the same logic state or the same sign, the output will be in the other way. Okay. Okay, since you guys kind of jumped the gun and brought this up, how do you make an analog multiplier? What is a Gilbert, sir? Who is Gilbert? Okay, let's just try to. He brought up an interesting idea that I'll apply a logic to the current source. Okay. Let's see what happens if we do that. Again, let's not worry about what voltage levels represent the logic of B. Okay, something is high and something is low. I hope you are all comfortable with this. So it's not like high is VDD and 0 is ground, right? We have to pick two voltages. Of course, for a healthy logic family, the two voltages should be sufficiently apart so that they can be easily represented, etc. Okay, but there is some voltage that represents B to be high and something else that is that means B is low. Okay, you have a class now at 3? You do. Okay, we'll stop here. But quickly, what happens if I apply some voltage here? Can I make anything useful out of this? What happens if B is high? High meaning this current source is active, that's all. What will be the function of this? Okay, and B is low. Both outputs are VDD, it's in some undefined logic state. Okay, let's have two of these. Let's say this is controlled by B bar. Okay, what will be the output here? So, and this is the output is not defined, and in this case B equal to 0, the first one output is not defined. Not defined meaning both will be at the same voltage level, and this, if this is Z equals C. So can I combine these in some way? I don't want to get, I want to get rid of this undefined stuff. Okay. Sort the outputs. What will that do? So basically what happens is when B is low, when this is low, this current source is inactive and nothing flows through these resistors. Okay, but that is the condition in which there is some current flowing through this. So I don't use two sets of resistors. I connect these two here. Okay, I connect the two differential pairs in parallel. Okay, so now I have a single output Y. I don't have two outputs. What is the function of that? What is the function implemented? So this is Yp and Yn. Okay, what? So it is B times A plus B bar times C. What is this function? It's a MUX. Okay, we'll see how to make this better. One of the problems is that this B and B bar, the voltage levels we have not defined properly. Okay, so we'll see how to make this better and make it more useful. Right? But this is also a very useful block. Not this, but something that will expand from this. Okay. Pardon?